Hello students, welcome to another lecture. So in the last lecture we had completed the problem of plate with hole. Now we could probably look into some numerical problems related to that, but let us first complete the syllabus, remaining syllabus, so that together we can discuss the problems that are pertaining to all topics. Now, before coming to torsion, what I would say is that till now, whatever topics we discussed using Timoshenko, all of those topics were strictly pertaining 2D problems. So we looked at two-dimensional problems using Cartesian coordinates. We also looked into two-dimensional problems using polar coordinates. So from today's lecture, we'll again go back to 3D. So today we will be discussing about, from today's lecture we will be discussing about torsion. So in your syllabus the exact word is torsion in prismatic bars. So what do you mean by prismatic bars? Well, prismatic bars is nothing but bars with uniform cross section. So the cross section can be anything, it can be circular, square, triangle, whatever, but the cross section is constant throughout the length of the bar. Now let us discuss the salient aspects of torsion. Now torsion is something all of you know what it is, right? So you might think, what is so complicated about torsion? The thing about torsion is, if you are taking a circular cross section, the study of torsion is simple, okay? But if you take a cross section which is non-circular, any cross section which is non-circular, including square, rectangle, triangular, or irregular shape, whatever, you have to deal with one extra phenomenon known as warping. So what is warping? That is what we'll also see in this particular lecture. Now so this is where you have torsion in the second edition, page 259. So as we said, the torsion of circular bars are fairly simple, and it is taken up in the earlier section. So it is, let me just go to that, 260, 239. So the torsion of or twist of circular cross sections is taken up in section 87. So here there is only some small discussion about that, because the problem of circular shafts or circular cross sections subjected to torsion is fairly simple. So we won't go for a discussion of this, but when we are when we are discussing the cross section of a general torsion of a general cross section, we will discuss some aspects of this as well. Okay, so let us continue with the discussion. So torsion was first studied in 1784 by Coulomb, and he arrived at the exact solution for circular bars or circular cross section bars. And further, the study on torsion was taken up by Navier in 1864. Okay, and whatever theory that was utilized by Coulomb, it was extended by Navier for other cross sections which are non-circular, because remember, Coulomb studied only circular cross sections, but Navier extended to other cross sections, and in process what happened was that he made an error. Okay, so whatever formulations he arrived at was have a little erroneous, in the sense that he failed to account for the phenomenon of warping, which is present in non-circular cross sections subjected to torsion. Now what is warping? We'll look into that. So what's happening is, you consider a cross section like this, any cross section, not necessarily rectangle as I shown, and imagine that its end is subjected to torsion. Okay, so this arrow I have drawn is just to show you the longitudinal axis. Okay, so this circular semicircular arrow is the torque that's applied at the cross section. So what is seen is, if the cross section is circular, then the plane section remains plane. So remember, plane section remains plane is an assumption we are used in the case of bending. So in the case of bending, it is easy to understand, we have seen it. In the case of torsion, if you try to imagine it, at this end of the bar you are trying to twist it. So as you are twisting, what we are expecting is the original cross section, whatever it is, it will remain as it is. Overall the cross section will twist, but the shape will remain same. Now what is found is, in reality, if the cross section is non-circular, strictly speaking, it is not, the cross section does not remain plane after twisting. There will be some deformation out of plane, like what I have marked here with the red pen. So in pure section you can imagine like this. So here actually it's an exaggerated view, but what you have to understand is, as you are twisting it, some portion of the bar will go out of this plane. So this is the plane, right? This is the plane where you have the twisting. So some portion of the bar will go out of the plane. So this phenomenon is known as warping, which is actually very important in all those machine parts and things like that. So you have to remember this term, warping. So when you are studying the torsion of non-circular cross sections, the general solution arrived should consider the effect of warping as well, which was not considered unfortunately by Navier in 1864. Later, the exact solution for non-circular cross sections, taking into consideration the effect of warping, was arrived at by Saint Venant. Okay, so you might have heard that name many times, Saint Venant. So Saint Venant is actually like a predecessor to Timoshenko. So he had made lot of contributions in solid mechanics, and even the Timoshenko textbook which we are referring now, you will see many references of the work carried out by Saint Venant. So Saint Venant found out the accurate solution for a general cross section bar which is subjected to torsion, which includes the effect of warping as well. Now, how Saint Venant arrived at the solution was that he employed a semi-inverse method. Now, semi-inverse method is a way of arriving at solution. So what happens is that in semi-inverse method, we don't know the exact solution. Okay, so we don't know the exact solution. So, but we start out with a approximation or assumption. Okay, this could be the solution. Okay, so we start out with a meaningful assumption, and as we work out the stresses and boundary conditions and things like that, it happens that the actual stresses in fact satisfy the equations of equilibrium, boundary conditions and things like that. So which means that whatever initial assumption we made about the solution is correct. Okay, so that is the general principle of semi-inverse method. So this semi-inverse method was employed by Saint Venant in arriving at the general solution for warping of any cross section. So let us discuss about the solution. So this is talking about the semi-inverse method. You can also read about it in the textbook. Some things are written here. Okay. Now let us discuss how we'll arrive at the formulations. So remember the torsion of circular bars. It is very simple. Okay, as I said, torsion of circular bars is discussed in section 87. So what happens is the only additional aspect that you have to consider when we move to non-circular cross section is that you will have the effect of warping as well. So there are two components now. Firstly, the solution will consist of a part which includes the effect of which is just like a circular shaft, right? Rotation of the cross section of the shaft, just like in the case of a circular shaft. And then to that you have to also consider the aspect of warping of cross section, which is like the out of plane deformation of the cross section or non-circular cross section due to torsion. Now if it is a purely circular cross section, this part won't be there, second part won't be there, and the solution is only first part. So let us look at how we can arrive at the formulations. So imagine a general element like this. So here I have drawn a general circular cross section. That is something I have done for simplicity, but you can imagine it as a general shape. It can be any general shape, okay? And let us assume these are our coordinate system x, y, z. So remember, I told you in the beginning of lecture, we are right now discussing the we will be discussing the three-dimensional aspects, right? We will be having all the three coordinate axes. So you imagine, this bar is something like fixed at this end, and you are subjecting it to a torsion at this end, okay? So it will twist. So as a result of that twist, you can calculate the deflections. So actually theta is twist per unit length. So what happens is, if you apply a torque like this, and suppose this end is fixed, so the total rotation of the cross section increases as you go with length, right? As z increases, the twist of any particular cross section will increase. So if you are defining theta as twist per unit length, now that definition is also something it was used earlier. Yeah. So if you are in the case of purely circular cross section, it was used. So if theta is twist per unit length, then at a particular cross section, total twist is theta into z, right? So theta is twist per unit length. So total twist at any particular cross section is theta into z. So if theta into z is the twist, suppose you are looking at one particular cross section. Suppose you are looking at this cross section. So imagine that you have a point here on the free body diagram of the cross section. So due to twisting like this, which is an anti-clockwise twist, or sorry, clockwise twist, this point will move to this location, right? So that will result in some displacement along x and y directions. So actually from this initial point to this final point, actually I have drawn a blown up view also here. What happens is, along x direction its coordinate is reducing, right? And along y direction its coordinate is increasing. So you can write using trigonometry and tan and the cosine function, you can write the net displacement along x direction is negative of total angle of twist into y, okay? Negative is there because x coordinate is reducing, right? And similarly v, which is displacement along y coordinate, you can write it as theta z, which is the twist into x. Same expression was used here, okay? So due to the twist of the cross section, this is your net displacement along x direction, which is u. This is the net displacement along y direction, which is v. Now what we said is that due to warping, okay, in general, as the cross section is not circular, you will have some out of plane deformation. So when you say out of plane deformation, remember the plane is xy. When you take any cross section, it is the xy plane. So out of plane deformation would mean there will be displacement along z direction, okay? So z direction displacement, we'll generally note it as w, okay? So we don't know what is the z direction displacement yet, because we are yet to arrive at the formulations. So following the principles of this semi inverse method, what we'll do is, see, one thing we can say, this displacement along z direction or warping is a function of twist per unit length. Okay, so because it's actually due to the twist that warping is happening. So if there is no twist, there is no warping. So larger the twist, more warping will be there. So w is a function of twist per unit length, as well as some function, some unknown function which we don't know yet, but a function which depends on x and y. Okay, because one more thing that was seen is that this warping is not uniform throughout the cross section. It varies with, you know, the location of the cross section. Anyway, so even if you don't imagine to that large extent, even if you just try to imagine it in a simple way, it is proportional to twist and it is proportional to some function. And for the most general case, you can imagine that the function is some function of x and y. Okay, so this is the displacement along z direction. So you have a displacement along x direction, you have displacement along y direction, you have displacement along z direction. So using the displacement, you can find out the strains using the fundamental formulas which were used or which I discussed in the earlier lectures of this course. Ex or epsilon x is dou u by dou x, epsilon y is dou v by dou y, epsilon z is dou w by dou z, and gamma xy is this, gamma xz is this, gamma yz is this, right? So you have u, v and w as general functions of x, y, z. So you can find out these strains epsilon x, epsilon y, epsilon z, gamma xy, gamma xz, gamma yz. So it happens that epsilon x, epsilon y and epsilon z is 0. Gamma xy also is 0 due to mutual cancellation, and only non-zero terms are gamma xz and gamma yz. Okay, so you have these strains. From the strains you can find out the stresses. So normal stresses, anyway, it is dependent on normal strains. So all the normal strains are 0. So normal stresses are also 0. Tau xy, so shear stresses, we know the expression, it is modulus of rigidity into shear strain, right? So tau xy is 0 because gamma xy is 0. Tau yz and tau xz, zx or xz, whatever, both are same. They will be there as non-zero terms, and to this you will multiply that with the expression of g, and that will be the expression for tau yz and tau zx. Okay, so this is the expression for stresses. So remember, this gamma is still an unknown. We don't know what is gamma yet. Okay, we have just defined it as a warping function, which is a function of, in general, a function of x and y. So from these expressions for stresses, some simple conclusions we can make. For example, there is no normal stresses. So remember, the bar is subjected to only twisting. There is only twisting and no other force. So in that scenario, there are no normal stresses. All the normal stresses are 0. So there are no normal stresses between the fibers of the cross section, and epsilon x, epsilon y and gamma xy is also 0. So epsilon x, epsilon y and gamma xy are nothing but strains in the cross section. So it is strictly only a function of x and y. So within the cross section there are no strains. Of course the bar is twisting, there is no doubt about that, but strains means there should be change in length. Okay, so strictly speaking, that is not happening on the cross section if you take individual cross sections. So the only non-zero terms are basically the shear stresses, tau x yz and tau zx. Okay, now what are tau yz and tau zx? You already know what this notation means, right? So in 2D coordinate system, when you talk about tau xy, it is either the no, stress along x direction on a y plane or stress along y direction on a x plane, right? That's what the notation of shear stress means. So similarly, here tau yz and tau zx are, suppose you take an element on the area like this, okay? So this area is along the outward drawn normal is along the z axis, okay? So this is a z plane. So tau yz and tau xz means tau zxz or tau zx, both are same, means that on this plane, which is a z plane, or any cross section on this plane is along the z direction. So on this area which is along the z direction, the stress along y direction is tau yz and stress along x direction is tau xz. Okay, anyway, we will discuss about this in detail in the upcoming lectures, so don't worry about this. But the point here to note is only this shear stresses are non-zero. So now the problem is not done yet, because we are yet to know what is phi or warping function. Okay, so I don't know if phi is the correct notation to use. Sometimes it is psi, but anyway, you recognize it by the symbol, not by the nomenclature. Okay, this is the symbol for warping function. Now we know that this body is in equilibrium, so it has to satisfy the differential equation of equilibrium. So this is the differential equation of equilibrium in 3D coordinates. Remember, this was a question for you to derive in your minor one. And also, even when we discussed the 2D problems using stress function and all, we started out with the derivation with differential equation in 2D coordinates, right? If you remember that. Anyway, so this is the differential equation of equilibrium. So whatever stresses you have here, it should satisfy this equation. Okay, see what we are out at it is we are trying to unlock this warping function. Okay, so we are trying to use whatever we have in hand to solve or to know more about the warping function. So these are the stresses, these are the differential equations of equilibrium. So you have the functions of these stresses. So let us substitute it into these expressions to see what other information we can get. Okay, so when you take the differentials, you'll using this, you will find out that first of all, let us assume that the body forces are zero. There are no body forces. Okay, and this will be zero, this will be zero, this will be zero. Only non-zero terms are del tau xz by del x and del tau yz by del y. So first two equations are identically satisfied. Okay, and third equation will simplify to this particular form: del square phi by del x square plus del square phi by del y square equal to 0. So it means that the initial warping function which we had assumed, okay, to determine this w, this warping function should satisfy this particular equation. Now further from this, the synthesis of this and things like that we will cover in the next lecture. Okay, so this lecture was basically a very simple lecture. We went through the introduction of torsion and we discussed the semi-inverse method, and we considered a general cross section like this. Again, don't confuse, it's not a circular cross section. I drew circular cross section just for simplicity, just like what is drawn here. Okay, and we finally arrived at that this warping function should satisfy this particular equation. We will continue in the next class. If you have any doubts, please let me know. Thank you.